So, yes, how to integrate JavaScript in your Rust program. First off, I'm Kettmeir. I work at Dino since 4.5 years, more or less. You can find me everywhere with the same handle, Cats. So, first off, what is Dino? I have to give off first the initial introduction to it. It's a JavaScript runtime similar to Node.js, but with more points in mind of security, TypeScript support out of the box, web APIs first. So if there's a web API, we will implement that instead of having our native APIs, unlike Node. This is an improvement just because so people that do front-end can more easily interrupt between back-end and front-end and not having to know different APIs. We have a bunch of tooling, testing, doc generation, benchmarking, linting, formatting, and a bunch of more, like compiling to a single executable and easy to distribute. But we also have Node compatibility. So any NPM package will work. Well, not every, most will work. And what matters to this talk, it's a modular code base. So there's a lot of crates that we will be taking a look at. So this is more or less the internal structure of Dino. It starts off with Rusty V8, which is the Rust bindings for the V8 engine, which is Chromium's JavaScript engine. And on top of that, we have Dino Core, which is a wrapper on top of that is relatively lightweight, but makes interacting with V8 much better. You don't want to interact with V8 directly because that's just a nightmare. Yeah, it abstracts a lot of information behind its structs and functions, but you still can access everything that you want and need, and makes using it a lot easier, and also includes a bunch of macros that we will take a look in a moment. Then extensions, that's like the different pieces of code or building blocks that you want to include in your project. So like you want a fetch API, just pull in the fetch extension. You want crypto, you want web GPU, just pull in those extensions. We have a lot of extensions. We have probably about 20 extensions, mostly being web APIs, but also individual other things like FFI support or reading from file system, etc. Then we have the runtime. The runtime basically just combines all the extensions and puts them together. It does provide some APIs on top of that are not available in extensions. For example, web workers, just because web workers integrate with every extension. So having that as a separate piece is not possible. So the runtime provides web workers, permission handling, and a few more bits and pieces, but those two are the main ones. And then the CLI is the CLI. So it includes all the extra tools, like I mentioned before, and yeah, JavaScript APIs for testing and benching as well. But everything else is included in the extensions. So what will we build? JavaScript runtime that can transpile TypeScript has a function to make a HTTP request, a console log, and do some file system operations in relatively few lines of JavaScript and Rust. Let's call it run.js. So first off, why would you even want to build a JavaScript runtime or integrate JavaScript in your project? Well, there's various reasons. I mean, a lot of users end up wanting to use JavaScript for like extension system. Like, I mean, GNOME, I believe, uses JavaScript for extensions, or like there's VS Code. Well, VS Code obviously is already written in JavaScript using Electron, but other IDEs, maybe Z, might be interested in using JavaScript for their extensions, etc. So extension building, running user code. So let's say you provide some serverless infrastructure and you just want to execute JavaScript code. That's also a good use case. There's a bunch of projects that already do exactly these things. So the use case is there. So first off, let's talk about extensions individually. So extensions are defined by a macro, and the macro has these options pretty much. And ops are something we're going to take a look in just a second, but they basically just declare a Rust function that can be called from JavaScript. ESM is ES modules that you can that are included with the extension. So if you want to have bindings to your Rust functions, you expose them via the ESM module files that you define if you want to have a specific layout of the API. JS files, scripts, so not ESM to include. This is a very niche use case. There used to be more of a use case, but since ESM is much more popular and we have integrated well with it, there's very little use cases to use the JS option. And deps. Deps declares if you want any other extensions to be defined as dependencies. This actually doesn't do anything under the hood, except just erroring out, oh, we didn't find the extension, like you didn't include the extension in your runtime that you asked for, but it's just a safety harness. If you don't include a dep, it's fine. It will not say anything. It's not like actual dependency, just a check that it exists. There's a few more options like config, lazy loaded ESM, state, and more. State is relatively useful, so you can define some state that you want to expose in the specific extension. Config is additional properties you want to declare to be available for the extension when you're initializing it. And lazy loaded ESM is if you want to lazy load ES modules, which has been, for us, a really good use case. For example, WebGPU. Very few people use WebGPU, but it's a massive amount of code. I think it's like 15,000 lines of JavaScript, just the bindings on the JavaScript side, and the Rust side is another, I think, 5,000 plus. And very few people use it. There is very little point to include it in the actual extension because loading files on startup is not cheap necessarily, especially large files like 50,000 lines of JavaScript. So by lazy loading them, you can just defer that to be then initialized when you actually call the API. So first call of the API will be slow, but it's a trade-off because we don't want to affect every user, even though like maybe 5 people use WebGPU. There's very little point. So ops. So we use the op2 macro. There used to be just op, but we've been refactoring a few things. Hopefully this will be renamed back to just op. And it defines a Rust function that you want to be able to call from JavaScript. So in this case, we have a simple reading file to string. And so in this case, it's an async op. So you need to give it an attribute of async. And then you see the first attribute macro, which is the string that refers to the return type, because a string can be represented in different ways, be it a box string, string actual, I don't know if we support references, maybe we do, and a few more cases of different representations of strings. So we just want to be sure that you attribute it with the correct return type. The same applies for parameters. There's a few differences between which ones need to be attributed for parameters and return types, but in general, it's a pretty much match one-to-one. And parameters can be pretty much not everything. Like if you want an object, you need to declare it as a struct in Rust and use Surder, which is relatively a slow path, which we don't recommend. But if you have a lot of options and objects you want to pass around, that's one way. Additionally, there's also something we call GCPG or something like that. I don't know who came up with acronyms, but they need to stop. It's terrible, but basically declares you can return one of these objects and mark it as that in the top attribute, and basically it represents a Rust struct that has a specific trait, the resource trait, and that can be passed to JavaScript, and then you can accept that again by a different op and accept it as a parameter. So basically, if you want to pass around some state through some struct that you need to have between specific ops, it does that. And then there can be also, besides string, we also have, you can pass a vector or slice or box U8 for array buffers. There is numbers, obviously, backends. There's a few specific ones that relate to the internals of Dino Core. For example, SMI, which represents the a resource ID, even though under the hood it's just an I32 or U32. It just abstracts it and makes it a bit clear that that's exactly what you're trying to specify. Because resources work by having a general state, which we will not see in this set of examples, but there is an op state, which is across all ops that you can access. And there's a resource table where you can add, remove various resources. And those are then accessed by an index, which is just an I32 or U32. And you can just pass that number around back to JavaScript much easier. And yeah, so let's look at a few examples of a few ops. So we have the read file that we just saw. So we just, in this case, calls Tokyo, reads files to string, and awaits it. Also, one more thing I forgot to mention is return types is, so in this case, we're using results, or it can be just a normal, like I could just return a string and unwrap. But error handling currently works by having a function that declares what an error type should map to JavaScript. So like, let's say SDIO error, I want to map that all to be just a type error. You can just define that in the function that you need to specify during the setup of the runtime. However, we are actually about to refactor this next week completely, that you can specify a trait on various errors and define the shape of the error, how it's supposed to be represented in JavaScript. So you could have, it represents the message, the error class, and additional properties you would want to define. For example, in Dino, for SDIO error, we show the error code as an additional property. So this would then allow you to relatively easily define everything, because until now, we've actually been using any error everywhere, which is not a good idea. It's been taking a month plus to refactor everything to be concrete error types, which is unfortunate, but it's definitely worth it, because at the end we've been doing some string, like turning the errors to string and doing some comparison on that, which is not great. But anyhow, another op is writing to file. So again, it's the same, just writing instead, and we're accepting 2 parameters this time. You can have as many parameters as you want. Then we have remove file. So in this case, you see that we have this fast attribute on the up2 macro, and that represents that the, this function can be called as a by a fast call in V8. Fast calls are basically just an optimized path that V8 can take. We error out if a function can be fast and it's not attributed with fast. So it's basically just a safety harness to make you more aware that a function can be called as a fast function. And then fetch. So very simple example. We take a URL, we do a GET request, we await it, we return the error, get the text, and return it back to JavaScript. Then we have a set timeout one, which basically just does sleep from the delay provided, and yeah, relatively straightforward stuff. So let's look at the actual JavaScript interface, which we will be representing as these few objects. So let's start off. First, we want a console log. We're going to be using core.print, which comes from the Dino global namespace. The core object is a built-in object that comes from Dino core that's always provided, and gives abstraction to a lot of things and availability to, for example, print or accessing actual ops, which we'll take a look in a second. So in this case, we're just having a console.log and a console.error that print out to, in this case, the Boolean at the end being if it's standard error or standard out, false being standard out, error, true being standard error. And then we're just doing some nice formatting and accepting objects, etc. to keep it relatively simple. Actual console log would be, I think, about 2,000 lines of JavaScript to properly implement, which is completely out of scope. Then we're adding a new global, run.js, and we're defining a few functions on that. So read file, write file, remove file, and fetch. And we're just calling core.ops and the name of the op, and we pass the actual parameters. And in this case, all of these return promises, since they're async functions on the Rust side. And then we have the set timeout, which just calls the callback after the timeout run out on the Rust side. And yeah. So then loading files. I assume it's quite small on the back. Can you read it or? OK, then I'll keep it as this. So loading files is done via a trait, a module loader, which defines where you can define how you want to load files. So in this case, we have a load function that's defined by the trait, and we accept a module specifier, which is actually just an alias to the URL instance, like a Rust URL create URL. And then we have maybe referrer, again, another URL that is the referrer for that URL. Then import if it's a dynamic import instead of a static import, but that doesn't matter for this case. And then the requested module type, if a specific type of module is requested. For example, if you're using the JavaScript static import with with attribute and, I don't know, using type JSON, then that will be marked as the requested module type. Else, by default, I think it's going to be always JavaScript. So we're just taking the module specifier, we're getting the file path for this provided module specifier, and reading it to string, and then just filling out the instance of module source, and then returning that. So we're specifying that it's a JavaScript type, and then making sure that it's a string, and returning other information. So we want to add TypeScript support, because everyone uses TypeScript nowadays. So that's all. That's not very much to add TypeScript support. Now, this is just type stripping. It's not type checking. Type checking is a whole other can of worms that is way too complex and will not be covered. But again, just reads the file to string. If it should transpile, which is based off the requested content type, so that we saw in the previous slide. So if it's TypeScript, we obviously want to see that it is, well, transpile it if it's TypeScript file. Then we're going to use deno.ast, which is one of our traits, which we provide, that is for, well, handling AST of JavaScript, which supports both TypeScript, JavaScript, and a few more types like JSON and WASM. We pass the module with a bunch of parameters, or specifier, again, the text, same, and other information we don't care, except the media type. Obviously, we want to specify what media type it is, because TypeScript is not just TypeScript, there's also TSX, for example. And yeah, we pass it, and then we transpile it. We leave everything default. We don't need much of the more granular, like, for example, TypeScript applicable options that TypeScript provides, and a few more specific options for the AST, rather for the transpiler itself. And return it into source and code, and have a fallback if it's not a TypeScript file, and then just, like the previous slide, we just return it plain with the module source. So our build script is relatively simple, but still a few things going on. So first off, we use a lot of snapshots, V8 snapshots. So snapshots are basically just like in any moment of V8 running, you can take a snapshot and store that as a file, for example, which is exactly what you do here. So first we define the extension, we call it run.js, and we specify the entry point of the JavaScript file that we saw earlier that defined the structure of the API that can be used. Then, and then we also have to re-specify, because first you have to specify always all the files available, and then which one is the entry point. Then we get the outdiff from cargo, and then store the run.js snapshot, and then we call create snapshot, well, get the path for the snapshot, and then create snapshot, which we have to specify a few options, and initialize the extension. And then we just write the snapshot path to the file path provided above here. So, yeah, let's actually set up the runtime. So in this case, we're then just reading the snapshot and defining an extension. So we have all the ops we defined and the name of the extension. We don't need to specify the JavaScript file because the JavaScript file was included in the snapshot. And then the actual runtime itself. So again, relatively small. And so we just get, for a provided file path that you want to execute, we just resolve the path and create a JavaScript runtime, which takes the module loader that we created earlier, which is in this case the TS module loader, the startup snapshot. So if we have a snapshot, in this case we do, we've specified that, and then the extensions. And in this case, we want to initialize all the ops. There is, again, like the ops state, so that needs to be initialized in there, but that's not needed to know. Just always initialize the ops. And in the previous case of the build script, we initialize ops and ESM. So we initialize also the JavaScript in that case. So then we have the JavaScript runtime, and then we just want to load the main module that we got earlier from the file path that was provided, and we evaluate it, and then run the event loop. You can evaluate multiple files if you want, but we're keeping it simple to a single file. We don't have much of a complex need. So, and then we just return the result. So in the end, it took 198 lines of Rust and 34 lines of JavaScript to create a JavaScript runtime that can be relatively easily be integrated in your project. And I mean, we can take a quick example look. So let's see. I have to quickly go out. You will not be able to see this easily, but we have an example.ts file, which just does a console log and then a set timeout. And this is a TypeScript file. We are not using any types, but just for simplicity. And then we can just cargo run the file. Sorry, it's so small, but it says out, waiting 2 seconds for timeout, and then out, hello world from timeout, because those are the parameters provided to the console logs outside the timeout and in the timeout. And yeah, that's pretty much it. Thanks for listening.
Leo Kettmeir.